Hello. So this is the second lecture on chapter 2. And here we're going to begin by covering modular exponentiation. In particular, let's say we want to compute x to the power of y mod n. And the problem that we're interested in is when x and y are very large numbers. So they could be 500 bits long, maybe 1,000 bits long, or even 2,000 bits long. And so we could never compute x to the power of y, because if you have something like 500 bits to the power of 500, a 500-bit number to the power of 500-bit number, the number of bits is enormous. However, x to the power of y mod n is still a number that's less than or equal to n. And so it's not possible to compute and then take the mod, but x to the power of y mod n is a number between 0 and n minus 1. So that it feels like there should be a way to compute it without having to actually compute x to the power of y. Let me first propose an algorithm that doesn't quite work for doing this. All we do, we start off by saying y is x mod n. And then we continue all the way up to y by multiplying in another x and taking mod n each time. So this works by the substitution rule, right? That we can kind of take this mod at an intermediate point. The substitution rule we covered last lecture. However, this for loop goes all the way up to y minus 1. And this number here could be 2 to the power of 500, right? Because it's if y is a 500-bit number, then this is 2 to the power of 500. So the for loop in this case runs 2 to the 500 times. If y is a 500-bit number. So not an efficient algorithm, right? This isn't going to work. But we're doing, the idea isn't bad here, and there's a better way to do it. And roughly speaking, so what I'm going to say is we can use instead a recursive algorithm. What we'd like to do roughly is to get up to let's say like y was a perfect square, like y was 64 or something like that. Then one way we could keep doing it, we could do this is by repeatedly squaring and taking the mod. So we could compute x squared, take mod n, then square it again, take mod n, square it again, take mod n, square it again, take mod n, and so on. And so for any number that's, if for any y that's a power of 2, this would work perfectly, right? The issue is that when y isn't exactly a power of 2, like let's say y is 2 to the 500 in this case, and it's, or let's say it's not exactly 2 to the 500, it's 2 to the 500 minus 739 or whatever, right? Then we have to do some like bookkeeping to make sure we square up to the right amount, and then we don't square for a bit. And there's actually a really elegant way to do this. And so it relies on a rule much like what we did in multiplication. And so we go like this. We say x to the power of y can be written as x to the power of the floor of y over 2 squared if y is even. And it's x multiplying that same quantity, x to the power of the floor of y over 2 squared if y is odd. Right? If y is even, then the floor of y over 2 squared is exactly y. If y is odd, then the floor of y over 2 squared is 1 short. So for example, if y is 50, then, or sorry, if y is 49, let's say, then y over 2 floored is 24. When you square 20, and then we end up 24 squared is 48, and then we get one more here, which brings us up to 49. Right? So if it's odd, we have to add on one or multiply one more x in. If it's even, we're good. And this yields a recursive algorithm, much like what we did for multiplication. So what we get here is 3 n-bit numbers, x, y, and n, and we're trying to compute x to the power of y mod n. We have a base case that if y is 0, then we get x to the power of 0, which is just 1. 1 mod n, as long as n for any positive n is 1, and so we return. Otherwise, we compute what's in the brackets. Right, so this is just this term right here. We're just computing it. And then if y is even, we square it and take mod n. If y is odd, we square it, and then we multiply by an extra x, and we take mod n, right? And we get to take this mod n because of that substitution rule, where x times y is equal to x prime times y prime mod n, or is equivalent to x prime times y prime mod n for any x equivalent to x prime, y equivalent to y prime. So correctness here follows directly from the rule, right? If you agree with this rule, this is just an implementation of that rule. Let's try and figure out the runtime. So the first thing you notice is that y is halved in each recursive call. And so it's reduced by a bit, right? So y is reduced by 1 bit in each recursive call. And so the algorithm terminates in n recursive calls, right? Where y is an n-bit number. It says here, y is an n-bit integer. Now, what do we do in each recursive call? In a recursive call, we evaluate an if statement. We check if y is even or odd. These are both order 1 operations. And then we either compute a square or we compute a square and then another multiplication. So if you think of squaring as just evaluating z times z, then that's 1 multiplication in the case y is even, or it's 2 multiplications in the case y is odd. So runtime per call. It's 1 or 2 multiplications. I'll say n-bit multiplications. And so the runtime per call is big O of n squared. And that means that the algorithm, since we have n recursive calls, each one being order n squared, it's n cubed. So alg runs in n cubed time. So not as good as multiplication, but still, I mean, much better than this algorithm right here, which ran in, exponential time in n. This is n here would be 500, and the algorithm ran at 2 to the power of 500 time, right? So 2 to the n time. Let me give you just a quick example to show you what's going on in this algorithm. And the thing that's kind of nice is, like I said, basically what you're doing is you're kind of just repeatedly squaring and taking a mod n each time, but you have to do some bookkeeping to make sure you get exactly to the right power, because it's not, the input y isn't a power of 2. So here's the case. Let's say we're evaluating x to the power of 20 mod n. So what the algorithm does is it instead evaluates x to the power of the floor of 20 over 2 squared, right? So to calculate this quantity here, it's going to instead calculate x to the power of 10, take a mod n, and then square it. To calculate this x to the power of 10 mod n, it's instead going to calculate x, take the floor of 10 over 2, which is 5. And so it instead calculates x to the power of 5 mod n squared mod n. Then in the next call, it instead computes x to the power of 2 squared, multiplies by an x because the 5 is odd. So then you get the floor, which of 5 over 2 is 2. And then finally, one more. Sorry, I should draw a little arrow. And then the last one is going to be, instead it computes x mod n and squares it. Okay, I've got lots of mod n's all over the place, but the point is to compute x to the power of 20 and instead computes x to the power of 10. It does that by this. So if we really go back up from the bottom, it starts here. It computes x mod n. It squares it. Then it squares it again, multiplies by x, squares that result, takes mod, squares that result, and then we're to there, right? So think about it kind of the way a recursive algorithm goes is it recurses all the way down to the bottom, and then it kind of emerges from this computation. So it goes up, right, to each successive level here. So square, square, square. So here we go. Square. Square and multiplied by x. Here we just square. And here again, we just square. And in doing that, we get perfectly to 20. And you can see we end up doing 1, 2, 3, 4, 5 multiplications rather than having to do 20. Okay. So just a visual example to kind of show you what the algorithm's doing. Next piece we need is the idea of computing the greatest common divisor. So this is the problem that you're given two integers, a and b, and you want to find the largest integer that divides both of them. So one possibility is just factor. So this is the problem. And one possibility is just factor them and find their greatest, and then multiply all their common factors. But that relies on an algorithm for factoring. And as I said at the beginning of this, I guess the last lecture is we don't know of an efficient algorithm for factoring. As far as we know, that's a hard problem. So let me give you just an example, though, of what the greatest common divisor is. So let's say we have A is 156 and B is 48. So A can be factored as 2 cubed times 3 times 13. B can be factored as 2 to the power of 4 times 3. And so the greatest common divisor, which we write as GCD of A and B, is the product of all their common factors. They have 3 2s and a 3 in common. So it's 2 cubed times, or sorry, this should be squared, right? 2 squared is 4 times 3 is 12 times 13. That gives you 156. 2 squared. And then here, 2 squared times 3, which is 4 times 3, that's 12. So the greatest common divisor of 156 and 48 is 12. There's actually a much nicer way to do this, which doesn't require factoring, and we can do efficiently. And it relies on something called Euclid's rule, which says that if A and B are positive integers, where A is greater than or equal to B, then the greatest common divisor of A and B can be computed as instead the greatest common divisor of A mod B and B. So I got the point of this is that I get to reduce the size of one of the arguments, right? A was bigger than B, so A mod B is a smaller number than A was. And so rather than having to compute the greatest common divisor of these larger numbers, I get to reduce the size of one of the numbers. And then what we're going to do is we're going to repeatedly do this, apply this Euclid's rule to repeatedly reduce the arguments inside the greatest common denominator until we get the result, essentially. So first, let me convince you that this result is true. The argument might feel a little bit, I don't know, unusual to you, but so you might have to pause here and go through it again. But once you kind of follow through, it's not so bad. But it takes a little bit of thought, I think, to understand what's going on. So first, let's just, so that we have a simple symbol for it, let's call the greatest common divisor of A and B n. So it's the largest number that divides both A and B. So we know then that there is a P and Q such that A is equal to P copies of n and B is equal to Q copies of n, right? Because n divides both A and B. And since A was a larger number than B, P has to be greater than or equal to Q. Now, if I just subtract these two, I see that A minus B then has to be equal to P minus Q times n, right? Just subtracting these two equations, or subtracting the second from the first. And so that then implies that n, right, A minus B can be written as an integer number of n's, an integer times n. And so n has to be a divisor of A by A minus B. Of A minus B. And so that tells us that n divides A minus B. So what I'm going to do actually is first I'm going to show that the greatest common divisor of A and B is equal to the greatest common divisor of A minus B and B. And then I'm going to use that result to show this one. So here we see that n divides A minus B and n divides B. That means it is a common divisor of both A minus B and B. So if it's a common divisor, the greatest common divisor has to be at least as big. Either it is just n or it's something even bigger than n. So that means that the greatest common divisor of A and B, which is n, is less than or equal to the greatest common divisor of A minus B and B. Also, let's show the other way, right? I'm now going to show the greatest common divisor of A minus B and B is less than or equal to the greatest common divisor of A and B. And then the only way for something to be both less than or equal to and greater than or equal to is for it to be identically equal. So also, if n divides A minus B and B, so let me actually call this. Okay, so no, if some number n divides both A minus B and B, then that means we can write A minus B as U multiplying n for some U, and I can write B as V multiplying n for some integers U and V, right? Because n divides both of A minus B and B. And now add these. If I add them together, then I get that means that A so what did I get from this? Now I have that if I have any number n that divides both A minus B and B, then it also has to divide A. And so this then implies that the greatest common divisor of A, B has to be greater than or equal to the greatest common divisor of A minus B and B, because n is a divisor of A minus B and B, or n is a divisor of A minus B and B, and it also has to be a divisor of A. And so then combining let me call this one 1, this one 2. We get the greatest common divisor of A and B equals the greatest common divisor of A minus B and B. Okay, so just to recap this second argument, we said suppose n, let's not say n is necessarily the GCD of A and B, but just n is any number, right? And let's say it divides both A minus B and B, then that same number necessarily must divide both A and B. So if n is the greatest common divisor of A minus B and B, it also has to be a divisor of A and B. That means that the greatest common divisor of A and B has to be at least as big as the greatest common divisor of A minus B and B. And here we have greater than or equal to, here we have less than or equal to. When we combine them, we get the identically equal to. Okay, and then the last part is just that finally, A mod B can be written as A minus KB for K equal to the floor of A over B. Right, that's just the definition of modulo. And so from that, we can basically chain together this argument. So the greatest common divisor of A and B is equal to the greatest common divisor of A minus B and B, which is equal to the greatest common divisor of A minus 2B and B, and so on, which is equal to the greatest common divisor of A minus k, b, and b, which is the greatest common divisor of a mod b and b, right? Because a minus kb is a mod b. And that is the end of this result. So like I said, a bit of a complex argument, but the main take home here, right, is that to compute the greatest common divisor of a and b, I can instead compute the greatest common divisor of a mod b and b. And so this is our algorithm. The one trick in the algorithm that you'll see is I take in two integers, a and b, and I'm trying to compute their greatest common divisor. And we assume that in this, that a is greater than or equal to b is greater than or equal to 0. So the first argument is bigger. And so, the first argument is bigger. So if the second argument hits 0, then we can just return the first argument, because the greatest common divisor of a and 0 is a. Otherwise, we apply Euclid's rule. And the only thing that we do is we swap the order of the arguments so that the first one is bigger, right? Because now, I mean, in our Euclid's rule, it says the greatest common divisor of a and b is the same as a mod b and b, but we swap them so that still the first argument is bigger because b is bigger than a mod b. And in doing that, we get to keep reducing both arguments rather than just shrinking one of them. So this is just an implementation of Euclid's rule. Runtime is kind of interesting though, because we have to try and figure out how quickly do the arguments shrink in this function. So the property that we need, which might not be that intuitive, but the argument is actually quite simple, is that if a is bigger than b, then a mod b is smaller than a over 2. It's kind of interesting, right? So what that's saying is that at every call, this argument, which, you know, this first argument here shrinks by at least half, like it's halved or more. So why is that true? Let's consider two cases. We break it up into two possibilities that cover everything. So case one, one option is that b is less than or equal to a over 2. Then it follows immediately, right? A mod b, by definition, is a number less than b because it's the remainder when I divide by b, so it's less than b. And by our case, b is less than or equal to a over 2. Okay. Case 2 then is that the opposite of this, right? So it's that b is greater than a over 2. But then in this case, we have that a mod b so remember, a is bigger than b, but it's less than 2b. So i.e. a, so we have b is less than or equal to a, which is less than 2b. So then a mod b is equal to a minus b in that case. But subbing in, we know that b is greater than a over 2. So negative b is less than a over 2. So this is less than a minus a over 2, which equals a over 2. So in either case, a mod b is less than a over 2, which is the result. So then this gives us the following runtime is I'm going to call Euclid on A, B. What does that do? It instead calls Euclid on B, A, mod B, which instead calls Euclid on A, mod B, right? The second argument becomes the first, and the first argument, and so, right, this argument goes first, and the other argument becomes B, or will be B mod A mod B, which is kind of funny looking. Like that. Right, this one goes to the first one, and the second one becomes the first mod the second. And now look at what's happened here. A in 2 calls has gone to A mod B. So A has gone to A mod B, which by our property is less than A over 2. And B is now B mod A mod B. So B has now mapped to B mod A mod B, which also has to be less than B over 2, since A mod B is less than B. And so we get that both arguments are at least halved every 2 calls. And so if every 2 calls we reduce each argument by a bit, and they're n-bit numbers to start, then in 2 n recursive calls, we're finished, right? So I'll say at most 2n. The numbers might actually go smaller than A over 2, so it might take fewer than 2n recursive calls, or and B over 2 in the second case. So here A and B are n-bit integers. Now, each call requires a division. To calculate A mod B. And so that implies order n squared per call. And so therefore the overall alg is, oops. The overall algorithm is order n cubed, where the number of bits in A and B is n. So that's what I've summarized down here. The runtime of this Euclid algorithm is n cubed. Okay, so we now have efficient algorithms for doing modular exponentiation and for computing the greatest common divisor. The final thing that I think we need is we need a way to generate large prime numbers. And we're actually going to also propose something called extended Euclid, which has a few useful properties. And then with those final components, we can talk about the RSA cryptography algorithm. And so that will be the things we'll build up in next lecture. So thanks everyone, and I'll see you in the next lecture.